What's going on, guys? Ch.13 here, back with another video, and today we're going to be discussing CBSE 10th grade physics, chapter 13, magnetic effects of an electric current. So without any further ado, let's get started. Keep in mind that this is part 1 of a 2-part series. So first, we're going to have a quick recap from chapter 12, electricity. So towards the end of the chapter, there was a section called heating effects of an electric current, and in that section we learned that when current is passing through a conductor, heat is released, and this is called the heating effect of an electric current. So the best example of this can be visualized when we charge our phones, and after a while, once we charge our phone, it usually gets hot, or even if we use our phone for a long period of time, the phone gets hot. So when the current is passing through, it releases heat in some form. This applies to smartphones when they're charging, water heaters, geysers, really anything. So from this we can also determine that when current passes through a conductor, a magnetic field is also created. But what is a magnet? What is a magnetic field? We'll be talking about that right now. So anything that has the ability to attract metal objects can be considered a magnet. A more rudimentary definition would be an object which produces a magnetic field can be considered as a magnet. And the magnetic field is the area in which the effects of the magnetic force is felt. Because the larger the magnetic field, the stronger it is, and it can be felt from further distances. If the magnetic field is smaller, depending on the size of the magnet, it can be felt that this force wouldn't be as magnanimous. So magnetic fields are usually visualized by magnetic field lines, which we can see over here. These are magnetic field lines, and we'll look at some properties of these field lines right now. So dense field lines indicate a stronger magnetic force. And keep in mind that these field lines always move from north to south, except in the middle where they move from south to north. As you can see here, in the middle over here we have north to south, and in the middle, in the center, they're going from south to north. The shape of this magnetic field is in the shape of concentric circles. And that's pretty much all you need to know about magnetic field lines. So how was it discovered that a current passing through a conductor would actually create a magnetic field? Well, it was actually discovered by complete accident through Oersted's Experiment. So Hans Oersted is a German scientist, and one day he just happened to leave a circuit on. He left the current running. He left the switch on, and he accidentally left a compass nearby. And if you already didn't know, a compass, it uses Earth's natural magnetic field, and it always points in the northern direction. But when he left the current on, he noticed when he came back a while later that the needle of the compass, instead of pointing north, it was deflected west. So you can see this diagram here. When he left it, the magnetic compass needle, which should usually be pointing to north, was deflected to be pointing to the west. And that was only when the direction of the current was anti-clockwise. And he noticed that when the direction of the current was clockwise, the compass needle was deflected to east rather than the west. So there's a basic understanding that took place stating that the currents actually produce a magnetic field. And the direction of the current can also influence the direction of the magnetic field. So to summarize Oersted's experiment, the needle of the compass would get deflected when an electric current passed, meaning that the electric current retains a magnetic field. So there's a few properties of current flowing through a conductor. For example, the strength of the magnetic field depends on the strength of the current flow. So if you increase the number of the strength or the amperes of the current, the magnetic field will also increase the strength. And the direction of the magnetic field depends on the direction of the current, and the direction can usually be determined by Fleming's right-hand rule, which we'll be looking at right now. So take your right hand and wrap it around so that you're making a thumbs up sign. So the direction that your thumb is pointing is the direction of the current, and the direction that your fingers are wrapping is the direction of the magnetic field lines. So you can visualize it here. Since the thumb is pointing up, that means the current is going upwards, and the fingers are wrapping around in an anti-clockwise direction. Even if you turn it around or rotate it and your finger is pointing downwards, then your fingers will be wrapped and it would be going in a clockwise direction. So that's what Fleming's right hand rule indicates. It indicates the relationship between the current and the magnetic field in terms of direction. So conductors are in various shapes and forms. There's straight conductors, there's circular coil conductors, and there's also solenoids, which we'll be looking at. But for now, let's just look at a straight conductor. So the conductor that I showed in the previous image, it's a thick straight wire, and it's actually a straight conductor, so it's the perfect example. So to find the direction of the current and the magnetic field produced by a current through a straight conductor, we can simply use Fleming's left-hand rule. For a circular coil, it's a little bit different. If we see here, this circular coil is the conductor that's carrying current. On the left side to the observer, as you can see, the field lines are going in an anti-clockwise direction. But on the right side of the observer, they're going in a left. So they're going in a clockwise direction. And in the center, they're almost parallel. So that's how the circular coil magnetic field lines move. And a solenoid is an insulated copper wire that's coiled in many turns. The most common example of this can be seen in traditional water heaters. So the magnetic field that's produced by this solenoid that's carrying current, it would be similar to a bar magnet, so north to south, except in the middle where it's south to north. And that's pretty much it. So you usually have, at least for this textbook, you have three options: either straight conductor, circular coil, or a solenoid. So the strength of the magnetic field is directly proportional. In a solenoid, it's directly proportional to the strength of the current, and the number of turns of the solenoid wire is directly proportional to the strength of the field. So if the solenoid has more turns, then the magnetic field will be even stronger. If it has less turns, it won't be as strong, relatively less stronger at least. Now let's talk about an electromagnet. So when a strong magnetic field is created when copper is coiled around soft iron articles, it can be used as a temporary magnet, which is also known as an electromagnet. As you can see here, we've coiled a copper wire around this article of soft iron and it connected it to a battery through some connecting wires. So once we provide a source of electricity and there's current flowing this conductor, this iron article becomes magnetized and it can attract objects, metal objects that is. So the thing about electromagnets is they're usually called temporary magnets because they're only magnetized when current passes through them. If we switch off the power source, then it becomes demagnetized, so it won't attract objects. So you may be wondering, what kind of application would this be useful for? It's useful for car magnets. If you've ever seen these large cranes that transport cars from one place to another. Essentially, normally, if you're gonna magnetize a car, it would be so strong that you can never demagnetize it. But they usually use electromagnets because it can easily be magnetized and demagnetized. So once you're done moving it, you just switch off the power source, and then the car simply just gently falls to the ground. So earlier I mentioned soft iron and not hard iron. Soft iron is used because its properties state that it can be magnetized and demagnetized easily, whereas hard iron, as it contains more carbon, it it becomes permanently magnetized, and you can't demagnetize or reverse the effects of the electromagnet. So the primary objective of an electromagnet is to ensure that it's a temporary magnet, and it could switch between magnet and demagnet quickly. But hard iron, in the case of hard iron, this won't happen, so soft iron is usually used. So, soft iron is used in smartphones, car magnets, and several devices that we see around us. So that concludes today's session. Thank you so much for watching. I hope you had a great learning experience. Stay tuned for part 2 where we'll finish the rest of the chapter. And until the next video, it's Ch.13 signing off. Peace.